In this section, we'll see the first compression method that already as it is shown here is competitive in applications. That's the Lempel-Ziv-Welch method, but you would probably better know it as variants of zip. And Lempel-Ziv is an entire family of compression algorithms. And this is one specific example that is arguably the cleanest to show. They all have similar flavors, and so it doesn't matter too much. But I definitely want to stress that whenever you use programs like zip, gzip, and their variations, they build on ideas around that and add more bells and whistles to it. But the core idea is what's coming up in this lecture. To motivate this, let's do a little toy example. Without much saying, without any further instructions, head over to Slido and tell me what the second to last line of that poem is. I'll leave the slide up, but this idea of presenting things in this activity is taken from Computer Science Unplugged, which is a lovely resource for explaining computer science concepts in a really approachable way and without computers, hence the name. There's many other cool things there, but this is from their compression unit. In case you're like me and you wondered what peas porridge would be, that's shown in the picture. I was told some Northern English dish, but I haven't yet found a local to confirm this. It's not Northwest. Yeah. And I'm not sure about 9 days old. Okay, votes are coming in. I don't know, let's briefly show them for the record. So what you've probably figured out without me telling you much, there's arrows that mean for certain boxes you have to go somewhere else and look up what the box stands for. And at least for these kind of extreme cases, like this very repetitive poem, you only get to write a small number of letters explicitly, and all the others can be referred to. The visual impression that you just store maybe a third of the characters is a little misleading because the arrows also need to be represented somehow if you encode it. But the key idea is that's what's behind Lempel-Ziv. Try to reuse things you've seen before. Okay? Yeah, of course, the poem reads, peas porridge hot, peas porridge cold, peas porridge in the pot, 9 days old. Some like it hot, some like it cold, some like it in the pot, 9 days old. Let's try to put that into slightly more structured language. What we said before is, what we looked at before is always looking at single characters. And already this motivating example from The Shining is showing that this is not exactly capturing all the sorts of repetitions that we find. And here's some examples where we have this repetition. I mentioned frequent words in English. But there's also other applications. If you have HTML websites, there's lots of tags that appear all over the place again. And these will be repetitions. And there you find bigger structures that are repeated many times as well. So to capture this, we need a different idea. Lempel-Ziv is a whole family of such compression algorithms. And as in the poem, you store things by referring to things you've seen before. What you can store more specifically in Lempel-Ziv or Lempel-Ziv-Welch is either a single character or a substring of the text of the part that you've already encoded. There are many variants of roughly the same idea, which essentially differ in how you find the thing you want to refer to and how you store the thing, how you store these pointers back to a different box. I just listed these because I think they cover many key phrases you might recognize, but this is not something you need to know, which one exactly is in which program. The variant I want to discuss is Lempel-Ziv-Welch. So there's a third person who invented a part of it, whereas Lempel-Ziv were the founding fathers of the idea, if you want. All of these Lempel-Ziv codes are variable to fixed encodings, which is supposed to mean a variable length portion of the text is encoded using a fixed size code word. So you will have a fixed size, a fixed list of things you can refer to, but the things they can refer to can be of arbitrary size in principle. A practical choice is having 12 bits or something around that for these code words, but that's not written in stone. What these methods do is they maintain a dictionary of strings or phrases that you can use in encoding the next portion of the text. That's why they are also sometimes called dictionary encoding. I'll denote this by D. Because the code words have k bits, you have 2 to the k entries in this dictionary. And each entry in the dictionary, they're just numbered, and that's the code word. Okay? So it's the indices in that dictionary. We always fill initially the first positions in the dictionary with the single symbols from the alphabet. We need that to get started. And then whenever we encode one portion of the text, we add something new to the dictionary. And maybe let me explain that in the picture. So we store something new. In this case, ban is a string I found in my dictionary before, so I use that. And I add to my dictionary the new string where I take one more character. So whenever I use a phrase, I insert into my dictionary a new phrase that's one character longer. And well, this is not clear here yet, but we'll make sure that whenever I take a phrase, this is also the longest phrase I could have taken. The trick here is to make this so that the decoder can also replicate the same process. And so you have to be a bit careful in doing that. But we'll see how that goes. Let's do an example, explain the algorithm on an example. And that might make it a little clearer how this works. So here we use the ASCII alphabet. So there's a quite long table for all the letters, etc., as you've seen on last time. And so I only show the ones that actually occur in the text. But the indices are as they would be for full ASCII. And then there's more entries in the dictionary that are currently empty. And they will be filled once in a while we're going. Initially, so what we do is always try to find the longest next portion of the text that occurs as a phrase in our dictionary. Sometimes we find several strings. In fact, we will most of the time find a shorter string that's already in the dictionary, and then a longer is also in the dictionary. We always take the longest match. So we try to find the longest string starting from the current position that we find in the dictionary. But initially, we have only the single letters, so we just take y. Its code is 89. And so that's the first code that we output. But we're not done yet. Remember, whenever we produce something, we insert a new phrase into the dictionary, and that is the phrase we stored plus one more character. So we insert yo into the dictionary as a new string to use in the future. Okay? Next step is a single O, because we haven't seen anything that starts with an O yet. So we just encode the single character again. O is here. but we do add another string to the dictionary, O plus one more character. All right. Next one, we haven't seen exclamation mark, so nothing happens, just a single character, same game. We insert one more phrase into the string, into the dictionary. Space is new. Again, we can't find a longer string, but we insert one for later. And now for the first time, something interesting happens. We have Y in the dictionary, but also YO. And so we use this as the longest match we can find and use this new code to represent that 2-character string. And we also add a new string to the dictionary, which is 1 character longer, taking the one new character from the text. Okay? U we haven't seen, so nothing interesting happens. The exclamation mark we've seen before, and it was followed by a space before. So we can reuse this 2-character string. And we insert another 3-character string where we have this combination. Okay? And now I guess you start getting the hang of it. The longest next thing is U. We find it here. So we use that code and we make the one bigger string part of the dictionary. There he goes, your. R we haven't seen, so nothing interesting happens. Then space, but we have seen space Y before, so we can use that again. One more. Okay, O we have seen, but OY we have not seen yet. So we can only use the O, but then insert OY. Then we see another yo. We haven't seen yo with an exclamation mark behind. That's it. And one more, and then we're done. If you're worried about how to find this longest string that is in the dictionary, a convenient way to store the dictionary for the encoding step is to store it as a trie. Now we'll have to modify our notion of trie because we essentially have not prefix-free sets of strings here. Indeed, all the longer strings by definition have a prefix that's already in the dictionary. And so we have to use an extended version of the trie where we allow values in the internal nodes. But other than that, that's a convenient way to find the longest match, because you start traversing the trie in the root with the next character and you follow down as long as you can. And the first character that doesn't match is the one that you have to add to the dictionary after that. The node where you stop tells you what character to use. So instead of this table, which is convenient to show to you, you want to use a trie to make this efficient. Here's that idea spelled out in code. The dictionary is stored as a trie here. We keep the next free code word, so the next row, the next index of the row in the dictionary. And we keep X as the previous phrase that we used, because remember, we have to insert that into the dictionary. Okay, so then we iterate through the text. That's this outer loop. We take the next character of the text. And then we ask the dictionary, have you seen whatever was the previous step plus this new character? And if so, then we go one step down in the trie. And we continue with the for loop. So we try to find the longest match. As long as we can traverse an edge in the trie, we keep doing that. When for the first time X was in the trie, but XC no longer is, we jump into this else branch. Then we get the code for X without C, which was a mismatch, and append that to the coded text, and we put XC into the dictionary because that's our new code word. And that's all for the encoding.